today by looking at some more variation questions and types of examples of Young's double slit experiment. Then we'll move on to a couple of more types of experiments in wave optics, which exhibits the wave nature of light through interference and diffraction. So continuing ahead with Young's double slit experiment variations. One example of a non-standard experiment or slightly different type of Young's double slit version is that we use a combination of two monochromatic lamps to illuminate the single slit. Okay. And rest of the things are standard. So this is the main screen, capital D suppose is given to us as 5 meters. Then this distance small d between the slits S1 and S2 is given to us as 2 millimeters. And this is the single slit. But now here we have a source which is emitting two separate wavelengths. So the primary source S or O, whatever. Okay, the primary source O in this case emits two wavelengths of light. Okay. Let's say lambda 1, which is lambda 1, let's say 400 nanometers, and lambda 2, which is 500 nanometers. So now we want to find the with respect to the symmetry point on the screen, which is say this point P0 is the symmetry point. So find the position on the screen Y with respect to the symmetry point P0, at which, first of all, there is a complete dark spot or a dark fringe. Assume the rest of the experiment is very standard. So there's two slits S1 and S2 are of same slit width. So they are creating light of the same intensity on the screen. So there is complete dark fringe. Okay. Then secondly, there is coincidence of lambda 1 and lambda 2's bright fringe. And third, lambda 1's dark fringe coincides with lambda 2's bright fringe. Just try this out, people. So rest of the experiment is the standard model. Okay, so you have the two opaque screens where you have the single slit S and the two slits S1 and S2. The single slit is symmetric with respect to S1 and S2, so it's passing through the symmetry line, and S1 and S2 are of the same width, and slit width as usual is of the order of magnitude of lambda. So these type of questions are pretty standard at JE level, and they're very easy to solve. Okay, once you get used to this, you will understand. There's nothing much in it at all. In fact, it's all formula based. For the first part, you have to just see that are there any positions at which the formula for dark fringe of lambda 1 coincides with the position that you get from the dark fringe formula for lambda 2. So you just remember that in a standard YDSE, the fringe width is given by the formula d lambda by d. Okay. So bright fringes are located at central maxima, the first maxima being above and below like this, the second maxima being like this, and the nth maxima being plus minus n times d lambda by d. And likewise, the dark fringes are the positions where so on and so forth. Okay. So what happens at the bright fringes in general is that the path difference, which is d sine theta, is equal to n lambda, or d into y by d is equal to n lambda. Whereas at the dark fringes, what happens is that the path difference is equal to n minus half lambda. So accordingly, the phase difference is 2n minus 1 pi, whereas here the phase difference is 2n pi. So if, as long as you're clear with this, rest of the things are very easy. Okay, so no dark fringes are coinciding. Yes, that might be correct because actually their ratio is odd even. No? So dark fringes will probably not coincide. Let's check anyway. So for the first part, dark fringes for lambda 1 are at positions, let's say y1 dark. Okay, let's say like this. So they are at uh, so this will be the fringe width for this will be 400 into 10 raised power minus 9 into 5 by 2 millimeters. So 2 into 10 raised power minus 3. So this will become uh, minus 7 minus 4 plus 1. So minus 3. Okay. So plus minus half millimeter plus minus 3 by 2 millimeter plus minus 5 by 2 millimeter, and like this plus minus say 2n minus 1 by 2. Okay. Whereas dark fringes for lambda 2 will be at say y2 dark. Now for this one the fringe width will become 5 by 4 times half millimeter. Sorry. So 1.25 1.25 millimeter. So this will be at plus minus 5 by 8 millimeters. then plus minus 15 by 8 millimeters, then plus minus 25 by 8 millimeters, like that, plus minus 2m minus 1 into 5 by 8 millimeters. So these are the individual positions of the dark fringes. Correct, Ganesh? You have got the same kind of result, I think. Yes. So if the dark fringes are to coincide, okay, so suppose, so understanding that this series is giving you the positions of the dark fringes for lambda 1, 400 nanometers. So they are occurring at these kind of positions, half a millimeter, 1.5 millimeters, 2.5 millimeters, and like that, 2n minus half millimeters. Okay. Whereas the second one, lambda 2 equal to 500 nanometers, they are giving you dark fringes at 5 by 8 or 0.625 millimeters, and 3 times that, then 5 times that, and 2m minus 1 times that. Like that. So if dark fringes, or if you can say a dark fringe of lambda 1 coincides with a dark fringe of lambda 2, that is a condition for, so condition for a complete dark fringe, that is zero intensity, is that a dark fringe for lambda 1 should coincide with a dark fringe for lambda 2. But that I think here will not happen, because the general formula for dark fringe for this one is 2n minus 1 into 1 by 2 millimeter, y equal to, and for that one it is some odd number into 5 by 8 millimeter. So if this is to happen for two odd numbers, that means the ratio of two odd numbers should be equal to 5 by 4. But this does not make sense, okay? Because ratio of two odd numbers cannot be 5 is to 4. So it does not exist. So a complete dark fringe does not exist in this particular case. Okay. Now likewise, you will see for bright fringes to coincide, bright fringes for lambda 1, the position of the bright fringes are, so obviously 1 2 will coincide at 0, okay, but millimeters, okay, because the fringe width is equal to 1 millimeter, okay. And for lambda 2, this d lambda 2 by d is 5 by 4 millimeters, or that is the same thing as 1.25 millimeters. So whilst the second wavelength's bright fringes are at 0 plus minus 5 by 4 plus minus 10 by 4, okay, plus minus 15 by 4 plus minus 5, okay, and like this, plus minus some integer m, let's say, okay, into 5 by 4. So for n is to m. Sorry, I got disconnected from the internet. Just give me a second. Yeah, so hope you're following up to this point, everyone. So, so we want the bright fringe of lambda 1 to coincide with the bright fringe of lambda 2. The condition for that is the y coordinate of this bright fringe should be equal to the y coordinate of that bright fringe. You can see the first time that happens when the fifth order maxima of lambda 1 coincides with the fourth order maxima of lambda 2. The next time that happens is when 10th coincides with 8th. Now the next time, so like that, it will happen when like some 5n and 4n coincide like this. So basically, fifth bright fringe of lambda 1 coincides with fourth bright fringe of lambda 2 at y equal to plus minus 5 millimeters. Okay. Then 10th bright fringe of this one coincides with 8th bright fringe of this one at y equal to plus minus 10 millimeters. Okay. Then 15th coincides with 12th at y equal to plus minus 15 millimeters. And like that, you can say the 5 capital Nth in general coincides with the 4 capital Nth at y equal to plus minus 5n millimeters, where n is the series 1, 2, 3, 4 natural numbers. And of course, even before all this, before I forget, also central maxima coincides. Not to forget that, very important, y equal to 0 coincides for both. Make a huge mistake if we forget about the central maxima. Right, so as you can see, these are very simple type of things. Like everything is just based on that simple proportionality concept that we were discussing last time, that on the screen the ratio of y versus fringe width is equal to the ratio of path difference with respect to lambda is equal to the ratio of phase difference equal to with respect to 2 pi. So if y is equal to some factor, let's say whatever, some factor alpha times d lambda by d, okay. If the position is this, then at that position the path difference will be equal to that same factor into lambda, and the phase difference will become the same factor into 2 pi. So this exists not only for natural number values of alpha or odd by 2 type of values of alpha, but for any fractional values also. Okay, uh, what about the third part? Are we getting any coincidence for the third part, where we wanted dark fringes of lambda 1 to coincide with bright fringes of lambda 2? So third part, that is at, that was how much now? That was 2n minus 1 to 1 by 2 millimeters, right? And bright fringes, they were at m times 5 by 4 millimeters. So 2n minus 1 to half should be equal to m into 5 by 4. So the ratio of an odd number to any natural number, we want it to be 5 by 2. So 2n minus 1 m, this will be 5 2, then 15 6, then 25 10, so on and so forth. So for this one, what will happen is that the third minima of lambda 1 coincides with the second maxima of lambda 2. Okay. For this one, eighth dark fringe or minima of lambda 1 coincides with sixth bright fringe of lambda 2. Okay, and this occurs at y equal to, for example, this is 7.5 millimeters. Yeah, whereas this one, this occurs at 2.5 millimeters. So you can see now this one's minimas, lambda 1 dark fringes, they were at y equal to 0.5 millimeter, then 1 millimeter, first, second. Oh, sorry, that's what I 1.5 millimeter, then 2.5 millimeter. So, then 3.5 millimeter, and so on and so forth. Whereas lambda 2's bright fringes, they were at 0, then 1.25 millimeters, then 2.5 millimeters, then 3.75 millimeters, and so on and so forth. So you can see that this one, the third dark fringe, this guy lambda 1, is coinciding with the second bright fringe of this one. Like that, if we write the series forward, we'll see that this also happens. The eighth dark fringe of lambda 1 will coincide with the sixth bright fringe of lambda 2 at 7.5. Okay, so this type of calculation is something that you just have to be a little bit used to. Okay. Now let's see another variation question. So in this question now, what is happening is that we are placing the screens, that is the first two screens with the slits and the final screen where the light interference pattern is observed. So these itself are placed symmetrically. Okay. So this is capital D equal to 5 meters. This is also capital D equal to 5 meters. And let us say this is the symmetry axis. So this point is our O. But interestingly, okay, this is not symmetrical. So these two slits S1 and S2 are symmetrical with respect to this. So this is D by 2, this is D by 2. Okay. But this single slit S, this is not symmetrical. This is at some D prime, let's say like this. Okay. And then you have the rest of the things standard. You have a source producing light of wavelength lambda. And of course, this is just a symmetry line. So this is a dotted line. Okay, so now given these things that small d is equal to 2 millimeters, okay, but d prime is equal to 0.5 millimeters, and of course capital D are given to you, and the wavelength of light used is 400 nanometers. So first of all, find the phase difference of light superimposed from S1 and S2 at the symmetry point O, and then from that find the position of the central maximum. So let's say that is YC with respect to that point O. And we'll do a third part also, but first work this out. Yeah, so Ganesh, you can calculate that value now. I want the phase difference in terms of pi. You'll get it as a factor of pi actually. So you have obviously calculated the path difference, from S1 and SS2 now. So that path difference now you have to convert to phase difference, which you've done 2 pi by lambda into that factor. But you will be getting a decent numerical value of it actually. So what is happening in this question is that these two slits, na, S1, S2 are not going to be in phase. Okay, these two slits S1, S2 are not going to be in phase, and that is why at the point O, the symmetry point, there is going to be some phase difference. So that phase difference is going to come from the phase difference of S1, S2 only. Yeah, that's correct. Some of the pi is correct. Okay. So from this slit to these two, if we calculate, we will get the path difference like this. So this, if you think about it, it's like a reverse of that calculation we have done earlier. This is small d. Okay. You take this small angle over here as theta, and this as d prime. So you can see that SS1 minus SS2 is basically equal to d sine theta, which is d into d prime by capital D. Yes. So then from here onwards, you can see up to the point O, there's no further path difference. So for the S1O is equal to S2O. Therefore, at O, the path difference of light coming from the two sources is just this only, SS1 minus SS2. Because the total path light is traveling via one path is SS1 plus S1O, and via the other one is SS2 plus S2O. So that is only this quantity, d prime by capital D. So you will see that that path difference is 2 millimeters, that is d, okay, into half a millimeter, zero point 0.5 into 10 raised power minus 3, divided by capital D, which is 5 meters. So that is coming out to be 2 into 10 raised power minus 7 meters, or you can say it is 200 nanometers. So there you are. The path difference is half a wavelength. So your phase difference, yes, correct, Ganesh. Very good. That's correct, Samadhi. Okay. So therefore phase difference is equal to pi at the symmetry point O. So now obviously my central maxima will be somewhere above here. Okay. So at the central maxima, my path difference should be 0. Delta x should be 0. So that means S1 plus S1c, this total path length minus SS2 plus S2c, this total path length should be same. Okay. So that means SS1 minus SS2 should get balanced by S2c minus S1c. So this we have just seen, it's already, we saw it's lambda by 2. So this should be equal to, if this y coordinate is yc, it should be equal to, like that, get it half a millimeter. And anyway, symmetry wise, you can see, no? I mean, this capital D and that capital D are same, so it's not surprising. Yes, Ashish, that's correct. 180 was the phase difference. So yeah, so the entire fringe pattern is shifted by half a fringe. You know, what is happening? O is becoming like your first order dark fringe because the path difference is lambda by 2, or the phase difference is, so if I bring down S from the symmetry point by half a millimeter below, I have shifted the whole fringe pattern upwards of O by half a fringe exactly. Yeah, Aditya, that's coming this way. That see, ये जो diagram है ना, the first part, just think of the reverse of this. So I've used that trick. Okay, just think of the flipped version of this. So S1 and S2 are here. Okay, and now S is over here. So understood now? So because capital D is very large compared to small d, यहाँ पे delta x equal to S1s minus S2s क्या हो जाता है? It will be d sin theta, which is approximately d tan theta, which is equal to d into y by d. But वही y के जगह अभी क्या है? It's y is actually equal to d prime. So that's how it's becoming d into d prime by d. Right, Aditya, this is clear, no? Okay. Now, one other part we can get in this question now is that you want to keep this arrangement, but you want to bring the central maxima back to the point O. So you want to keep some kind of refracting slab in front of one of the slits. Okay. So now, third part of the question is, if a refracting slab which has a refractive index of, let us say, 1.05, it's a very odd kind of slab, nearly made of air kind of thing. Okay. So hypothetically, it has a refractive index very close to 1. Okay. Of thickness, let's say T, is used in front of one of the slits to bring the central maxima back to the symmetry point O. Find the thickness and which slit should it be placed in front of? Slit S1 or slit S2? Yeah, so see now what is happening is we want that SS1, okay, plus S1O optical path length should be balanced with SS2 plus S2O optical path length, so that the optical path difference should be 0 at the point O. So phase difference should be 0. Okay. So now we already know that SS1 minus SS2 is a positive quantity. In the above diagram, yeah, we'll just discuss. Okay. So you can already see that SS1 is longer in length compared to SS2. So that means the light from S via S1 is taking longer to reach the point O. So we have to slow down the second one. So if we have to slow down the second one, the slab has to be placed here. So the slab has to be placed in front of the second slit. So now let us say we are placing the slab here. So then my above equation will correspond to this, that this thing which we had calculated, d prime by capital D, this should become equal to mu minus 1 into the thickness. Okay, because S2O's optical path length is greater than S1O's optical path length by that much. So that's it. So this we had seen was lambda by 2, 200 nanometers should be equal to 1.05 minus 1 into the thickness. So the thickness should be equal to 200 into 10 raised power minus 9 divided by 0.05. So that is 20 by 5 into 10 raised power minus 8 plus 2, right? So 4 into 10 raised power minus 6 meters. So this is the answer that I am getting, 4 microns. And that is like the kind of thickness that a sheet of paper has, microns, or polythene, something like that. Just check my calculation, all of you, but this is what I am getting because I have taken the refractive index as 1.05, remember, not 1.5. I told you it's a hypothetical one, it's not like glass or something. Okay, good. Okay, so this can be like, one of those polythene sheets which is few microns thick. Okay, good. Now let's move on to another variation experiment of IDSC, and this one is called the Lloyds Mirror experiment. Lloyd spelled with a double L. It's a name, so anything goes. So Lloyd's Mirror experiment. So this what it does is it establishes two things. One is, of course, it shows interference of light, but it also shows the nature of light waves being transverse. So it demonstrates the transverse nature of electromagnetic waves of visible light. Okay. via interference, okay, and phase inversion during reflection. So if you go back to transverse mechanical waves, you will recall that we had seen that reflection by a rigid boundary results in phase inversion. Now light will show the same phenomena in the experiment. So in this experiment, we're not dealing with mechanical waves, we are dealing with electromagnetic waves, but they will show the same phenomena. So let's understand how that works. So what we have here is a plane mirror. And by the way, these kind of experiments are very difficult to demonstrate because for a mirror to be perfectly plane and the surface to have hardly any imperfections, very difficult to fabricate. But anyhow, now you have a screen on which you are observing the interference pattern. And this is a plane mirror. And what we also do is place an opaque screen over here with a single slit this time. Yeah, I'll give it to you to write down, don't worry. So there's a single slit here, which where again the slit width is of the order of lambda and all that, and monochromatic light which is incident on this coming from some source, light of wavelength lambda. So what we observe on the screen is interference pattern. Okay. So on the screen, an interference pattern is observed, alternately bright and dark fringes. Bright and dark fringes. Okay. So again, if this distance is capital D, okay, and this time this distance here is small d, then what we see is that at any point on the screen, light reaches via two paths. Okay, one is the direct and the other is the reflected. And the reflected path of light is such that you can assume it is coming from a imaginary or a virtual reflected source, like a image kind of source. So at this point, light will be coming directly and then it will be coming by reflection. Now this reflected beam, it will appear to be coming from an imaginary slit, which is the image of this one, S prime, okay, which is at the same distance d below. So once again, the experiment is done such that capital D is very large compared to small d. So if this is y, okay, so at this general kind of point P, if this point from which reflection is happening, so the path which is direct, okay, that is SP, and the path via reflection is like S prime P, because this and this are congruent triangles. So This actual path length from S to the point on the mirror, and then from that point to this, is the same as the direct path length from S prime P to S prime to P. Okay, so the path difference becomes this S prime P minus SP, which we can approximate as 2D into Y by D. Same kind of thing. Because if we take the angular position of that point as theta, you can see that S prime P minus SP is approximately 2D sine theta, is approximately 2D tan theta, which is 2D into Y by D. Okay. So this becomes the path difference. So but what we will see is that the phase difference at the point P will actually be 2 pi by lambda into this path difference plus or minus of pi. So why that additional term occurs is because the reflected beam has a phase inversion. So the additional plus minus pi term is due to phase inversion from reflection. Okay. So therefore, the positions for bright fringe are at delta phi equal to 2 n pi. So that means 2 pi by lambda delta x should be odd multiple of pi. Okay. So that means delta x should be odd multiple of lambda by 2, or so the position of the bright fringes, they come out to be y equal to like this. Whereas dark fringes, they should occur at positions where phase difference is 2n plus or minus 1 of pi. So 2 pi by lambda delta x plus or minus of pi should be equal to 2n plus minus 1 of pi. So delta x is n lambda. So y becomes 0 d lambda by d, 2 times d lambda by d, like this, n times d lambda by d. So it's a very interesting situation. Okay, you see the same kind of, oh, but this is 2d, just one mistake. Everywhere I've written small d, now replace it with 2d. Just replace it with 2d, because the distance between, that sources s prime and s is 2d, this kind of thing. Okay, so yeah, I'll just minimize and let you go through this. Yeah, Jatin, the phase inversion factor, like we had seen transverse pulses on a string, when they reflect from a rigid boundary, they come back with phase inversion. So the incident wave versus the reflected wave, there's a phase difference of pi. Phase inversion means phase difference of pi. So same thing is happening at the surface of the mirror. The incident beam and the reflected beam, there's a phase inversion that is happening. So that is why between the direct path SP and the reflected path through the mirror, there is an additional phase difference factor of pi, apart from the path difference factor 2 pi by lambda delta x. Okay. Yes, sure. Sure. I'll show you the heading. It is called the Lloyds Mirror experiment, and just a second. It's called the Lloyds Mirror experiment, and it is for demonstrating not only interference of light similar to YDSE, but also it shows you that light is a transverse electromagnetic wave, because the interference pattern that we get when we match the experiment with respect to the theoretical calculations that we do, it proves that there is phase inversion at reflection. So phase inversion ho raha hai at reflection at a hard mirror surface means that it cannot be longitudinal wave, it is transverse wave. Because longitudinal waves, you'll remember the pressure waves in case of sound, they have the reverse phase relationship. That reflection at a hard boundary does not involve phase inversion. Reflection at a flexible soft boundary involves phase inversion. So if reflection at a hard boundary is resulting in phase inversion, that means it is showing the character of transverse wave, not of longitudinal wave. Okay, so hope this part is clear. So now interestingly what it is showing you is that right at the corner point where y is equal to 0, we will get a destructive interference, or we will get, a dark fringe. So it's worthwhile considering why that happens, and I'll explain. So anyway, first to write down the mathematics of this. So the position of the dark fringes and the position of the bright fringes. This is the dark fringes. Okay, so this was the point I was referring to, that y equal to 0, it is giving you a destructive interference point or a dark fringe. So if you really think carefully about why exactly that happens, is you'll realize that at y equal to 0, you are getting like a very precise kind of overlap between a direct wave traveling a certain length from that path length from that source S, and a reflected wave that is just reflected exactly at that point where it meets the screen. Okay, and therefore it has traveled the same length as the direct wave. Let me explain. So at this point, what is happening is that you will effectively feel like there is only the direct wave reaching that point. But you can say that any beam, part of it gets reflected just before hitting the surface, and part of it hits the surface directly. So there's an overlap of direct and reflected light, but at path difference 0. Okay, at this position. So the direct beam and the reflected beam, they have a phase difference therefore of pi. So that results in destructive interference. So this was the very conclusive evidence that phase inversion occurs from this actual experiment was done. Okay. And then you will get your first bright fringe. So you'll get a dark fringe over here. Then you will get the first bright fringe at a distance which will be half the fringe width. So that fringe width over here will be d lambda by 2d, because this distance is d. Okay, so hope this Lloyd's mirror experiment concept is clear to you. Now there will be some more types of variations we will see of optical experiments where something like YDSC is happening. So one other good example of that is this one, where what we do is a thin lens, a thin lens L, let's say. Now it is cut about a plane like this. So cut by a plane bisecting it, okay, along the principal axis. So that gives us two half lenses like this, L1 and L2. Now next what we do is we place L1 and L2 but with some gap between their individual principal axis. So we place these two half lenses like this, but after pushing a gap between them, okay. And then what we do is we also plug in this gap with some opaque material, so light cannot go through this part. This is opaque. Okay. Now let us say we have pushed these apart by a small distance d like this. Okay. And now what we are doing is we are placing that kind of situation. We have that opaque screen with a single slit, okay, S, and monochromatic light coming from this side. So this is placed at some distance x, okay, where x is basically, let us say, between f and 2f for these lenses. So obviously if this lens has focal length f, these two half lenses will also have the same focal length because radius of curvature has not changed. Okay, and this is on the symmetry line. Okay. So S is equidistant from these two. So what will happen is now the light from S, the monochromatic coherent light that falls on these lenses, it will create two images. So it will create two images of S. Let's say over here S1 and over here S2. Okay. So now any distant screen placed on this side, suppose you place a screen at a distance y, on that screen this S1 and S2 will become like the two sources illuminating it. So lenses or half lenses L1 and L2, okay, produce two images of the slit S as S1 and S2. Okay. Now these images S1 and S2, they become coherent monochromatic sources in phase. Okay. So then they produce an interference pattern on the screen. Okay. So for example, Just make this diagram first, then I'll take a numerical example of this. And if you've taken the diagram down already, let's do this. Suppose the focal length of that lens is, let's say, 3 meters. Okay. And the gap that we have placed between L1 and L2, that small d is, suppose, 0.5 millimeters. Okay. And the distance from the slit to the vertical or the common pole axis of the two lenses, that one x we have taken, is, suppose, or let's take this smaller. Instead of 3 meters, let's take this as 15 centimeters, and x is, let us say, uh, 20 centimeters. And now the distance of the screen from this one, this y, is equal to something pretty large. Let's say it is 12 meters. Okay. And let's say the wavelength of light we are using is 500 nanometers. If you want to find the fringe width on the screen, delta W, the fringe width on the screen. Okay. So try working this out. This is more a geometrical optics question now. That using the lens formula and understanding the position of the principal axis of each of the half lenses L1, L2 with respect to that single slit acting like the object, you have to find their images S1 and S2. And from that you can find the distance between the images, and you can find the distance between S1 and S2 with respect to the screen, and then use your YDSC formula. So as I said, it's more of a geometrical optics question. Just work this out quickly. Okay. Yeah, Ganesh and Somadeep, what is your answer? Ganesh, your answer seems to be correct. Yes. For the fringe width, let me just check. Okay. So first of all, let us understand the position of the images. So, like, we have one half lens like this. This is its principal axis. Okay. So the single slit that we have over here, S, This is at, okay, this is at d by 2 below, and that d by 2 was 0.25 millimeters, and it is at x from this. Okay, so its image will be somewhere over here, where this is, let's say, y1, and this is the image distance v. So let's work this out. So 1 by v minus 1 by u, and 20. So minus 20 is equal to 1 by plus 15. So we're getting 1 by v as 1 by 15 minus 1 by 20. We're getting v as plus 60 centimeters. And we are also getting y1 as the mod of magnification times d by 2. So magnification factor will become how much? 60 by 20, or 3 into d by 2 is how much? 0.5. Sorry, 0.5 by 2 d is this. Okay, so this is becoming 0.75 millimeters, correct? So that is this y1, which is the distance from here to here. This is y1 from the principal axis to this distance is y1. So now if you look at both the, so hope this part is clear to all of you. So now just apply the principle of symmetry here and understand how this thing is occurring. Okay. So this is one principal axis, this is the other one's principal axis, and at the symmetry point you have the object, which is the single slit. So one image is formed here, one image is formed here. So this is your y, which is 0.75 millimeters, and this is also 0.75 millimeters. So whereas this is already small d, which is small d was how much? 0.25 millimeters. Okay, that is the thing. And now the screen is here, where you can see that this distance we just saw is 60 centimeters, and this whole distance was, how much was it now? 12 meters. So that's 1200 centimeters. This one. Okay. So coming back to this arrangement now, so you can see the equivalent of small d is this distance here for your YDAC. So that small d for the YDAC part is working out to be, oh sorry, this one is zero point 0.5 now. Yes, that's correct. This is zero point 0.5. Right, Ganesh. Okay. So small d is becoming 0.75 plus zero point 0.5 plus 0.75. So that is becoming 2 millimeters, is it? Okay. And capital D is becoming 1200 minus 60, or 1140 centimeters. So you can also write it like this. So the fringe width is going to be d lambda by d. So that is, okay. It's going to be some strange kind of number like this. So 2.85 millimeters. This is the fringe width that I'm getting. Just check the calculation. So to be a little extra careful about all the calculations, you might have taken capital D as 12 meters by mistake, but remember that was the distance from the screen. Good mistake. So remember that you have to subtract that 60 centimeters, from the total distance from the screen, because your capital D will be this one actually. It is from S1 S2 to this. This is your capital D for the equivalent YDS. So there's nothing in these questions. Okay, it is just about trying to induce mistakes during the exam. Anyhow, so this interestingly completes our portion for JE Advanced for wave optics, because in wave optics in JE Advanced we have only interference, and that too as a named experiment we have only YDSC, but along with YDSC there are all these you can say these modifications of YDSC, or these modified versions of YDSC. Now there is one more experiment that is there, but only in JEE mains syllabus, and that is the single slit diffraction experiment. Okay, so we will discuss that in detail just now, and with that we will complete wave optics today. So that next lecture onwards we can start discussing modern physics, and modern physics is a very easy and reliable sort of scoring kind of portion of physics. So effectively we have reached the very end of your syllabus, and I think pre-Diwali we should be able to finish at least the entire JEE advanced syllabus. Maybe a couple of things for JEE mains like semiconductors and things like that will remain. Okay. Uh, we modern physics we will do the first we will do Ganesh the four topics which are common for mains and advanced. That is photoelectric effect, Bohr's model, X-rays, and nuclear physics. And these topics are individually very small, so we might be covering two of them in a single lecture like that. So okay. So we'll just take a quick break, 5 minutes or so, and then we'll come back with single slit diffraction. Now, why I want to do single slit diffraction before I get into modern physics is one, because it's wave optics and we're already doing that. And the other thing is, by understanding the single slit diffraction experiment, we will understand a little bit better about YDSC also. We'll understand things like why the slit width should be lambda in YDSC, and what happens if I make the slit width smaller than lambda or larger than lambda, how that affects the interference pattern and all that. So it's a little bit important in that sense. Okay, so just take a 5 minute break. We will continue ahead with single slit diffraction. Okay, so let's get back to it. So the next thing we will study is a demonstration of diffraction. So diffraction is a phenomenon that can be described in context of two types of observations. Okay, one is diffraction is the bending of a wave around an obstacle. Okay. So for example, we have this situation, you have a source of sound, and you have an obstacle which is made of high density material. So sound cannot penetrate it. So this is non penetrable. Okay. But you have an observer on this side, so the direct path of sound is blocked. We can see direct path of sound is blocked by the obstacle, but still the observer detects sound. Okay. Especially low frequency sound. Okay. So why that occurs is because of diffraction. So once again, if you understand in terms of Huygens principle, what is happening is that as a wavefront like this is there, every point in the wavefront becomes a secondary source which is generating its own wavefronts. So even though these ones are reflecting back, okay, but these ones are creating sound in such a way that an observer here is going to be in the path of some of these secondary waves which are generated by all of these. Okay. So if you think in terms of Huygens principle, okay, diffraction makes perfect sense. But for diffraction to be effective, okay, if the size of the obstacle is of the order of or less than wavelength, then diffraction is effective. Okay. Otherwise, if the size of the obstacle is very large compared to the wavelength, then diffraction fails. Does not occur significant. Okay. So that is why, for example, this thing low frequency content is diffracted easily. Low frequency means large wavelength. Okay. So if you're hiding behind a cupboard and on the other side you have a speaker or something creating sound, from the other side of the cupboard you will see the quality of sound changes. You hear more low frequency content and the high frequency content is kind of cut off. So the balance of sound changes. So if, for example, you're hearing voices or somebody's vocals, the timbre of the sound changes because the low frequencies are more clear to you via diffraction, whereas the high frequencies are getting cut out. So there's some kind of filtration process happening of frequencies in diffraction, or sound, for example. Now, the same thing can happen for light also, and we'll discuss. So that is one situation of diffraction. But this is not what we'll observe in the wave optics part. The other part of diffraction is diffraction is the spreading, okay, of a wave through a small aperture or opening. Now, this is the kind of thing which we will observe in wave optics situation. Okay. So anyway, just write down the first case, few of the details if you want to. Then we'll come to the second one. Okay, so as the waves propagate from this, these are the wave fronts. Now the obstacle blocks the wavefronts, the secondary wavefronts for some of the points, but around the obstacle there are other secondary wavefronts, and they create secondary, secondary sources, and they create secondary spherical wavefronts. And ultimately, those are able to reach the observer. So even though there's an obstacle cutting the direct path of sound or direct path of waves between S and O, but the waves are able to bend around the obstacle because of that nature of secondary wavefronts and secondary point sources in the primary wavefront. So that phenomena is the demonstration of diffraction over here. Now the second case of demonstration of diffraction is, again, you can visualize that water tank experiment, okay, where what we are having is a surface of water. And on that surface of water, so firstly you have like the surface of water. Okay, this is a water surface top view, but there is a wall in between. So there's a thick wall in between, but with a small opening. So there's a small aperture in the wall with a narrow slit, like a vertical slit. So that is acting like the aperture. So this is something very easy to visualize. And again, Huygens principle allows us to make sense of what we visualize also. So suppose we drop a stone or a pebble onto the surface of water on this side. So we are creating disturbance at this source kind of point. So it's creating these kind of wavefronts. Okay. But we will observe that now on this side wavefronts like this propagate. So if wave was a phenomena that just travels along straight lines, then a point like this over here should never experience any disturbance because there is no direct path between S and P. But you do know that if you have a piece of, you know, a twig or something floating at this point in the water, initially it is still, but I create some disturbance on this side, eventually this twig will also start floating. So that means the disturbance created on this side at S is going to somehow create disturbance at the point P, even though there is no direct path for the wave. So that happens because the wave sort of, it oozes out through the aperture. It is able to bend through the aperture. It spreads through the aperture. Now that spreading effect is what we call diffraction again, and that again occurs because of the nature of wave propagation. At every point in a wavefront acts like a secondary source. Okay. So this spreading of the wave through a small aperture, this is also diffraction. So over here we'll see that the point P will experience transverse surface waves due to diffraction through the aperture. Okay. So now the single slit diffraction experiment in light is the experiment used to demonstrate that phenomena in visible light or electromagnetic waves. Okay. So single slit diffraction experiment. This is a wave optics experiment, and it demonstrates diffraction of light through a narrow slit or aperture. Okay. So right from design of the experiment to the explanation, you will see that again Huygens principle will play a very vital role in trying to understand how exactly the experiment is happening. So let's visualize. So the experimental setup is again like this. You have basically two opaque screens, one with a very narrow slit, and now one with a comparatively wide slit. So I'll come to that. Okay. And then of course you have the main screen on which you're observing the diffraction pattern. Oops. Okay. And we'll get back to that. So that one is the main screen, whereas in between we have another screen on which there's also going to be an aperture. Before that, this is like the symmetry axis. Now here there's going to be a single slit which is comparatively wider. It's not a YDSE type of slit. So the slit width here is something of huge importance, and we'll discuss about that. So this is the main screen on which the diffraction pattern is observed, whereas these are opaque screens. Okay. Now this one is called this S naught. It is a very narrow slit. Okay. YDSE type slit, where the thickness of the slit is approximately lambda or even less. Whereas this one is also a narrow slit, but compared to this, it is much wider. So this one is a slit. So S is a slit of wider width compared to YDSE. So typically the slit width E is something of the order of, let's say, 50 lambda, where lambda is the wavelength of the monochromatic light that we use. Okay. Now here we have the primary source, which is monochromatic, but of course we cannot use the primary source to create coherent waves. Hence this single slit is there, which creates coherent monochromatic waves. And now this illuminates this slit. Now this slit, because it is wider, it is going to create a more difficult kind of pattern here. It's going to create this kind of pattern. that kind of thing. So all those like imaginary secondary point sources are going to result in the spreading of light around over here, and on the screen finally we will see a pattern, and this pattern will also be alternate dark and bright, but quite different compared to IDSC. So we'll understand why this is the case. So we'll make a quick note of the of the apparatus. Now the important things to keep mindful of here is that first of all, P is a primary monochromatic source of wavelength lambda. Okay. Now S naught is a narrow slit, so it produces coherent, that is in phase, monochromatic light waves. Okay, and these light waves illuminate S, which is a wider type of slit, where the slit width A is typically of the order of 50 lambda or 20 lambda or something like that. Whereas this one is a narrow slit, so its slit width is of the order of lambda. Okay, so that is the significance of the experiment. And of course, we have this distance again denoted with capital D, and capital D is going to be very, very large compared to small a this time, the slit width of the single diffraction slit. So we are going to look at diffraction happening through the single slit S. So this is clear up to this point. Okay. Now let us first discuss what we observe on the screen, and then we will come to the calculation part, how to understand or make sense of that observation. So if we actually do this experiment properly, we will observe the observation is like this, that on the screen there are alternate fringes. Okay, so fringes again mean those horizontal bands of light of bright and comparatively dark intensity. But the central bright fringe is wider, okay, and also much brighter than first order and second order and onwards bright fringes. Okay. In fact, what we observe over here is that if we were to draw a graph of position on the screen versus intensity, so in a YDSC we had seen it was like a cos square kind of graph. No? Intensity versus position. So in context of your screen, again, this symmetry point is your O, and at any point over here, this is Y. Okay. So we are now plotting the intensity of light at a point versus Y. So that will be this kind of a graph, very unlike YDSC, a very bright and wide central maxima, and then comparatively much less in brightness maximas, and the brightness of the maximas drop. And we'll also see that this width is going to be two times in comparison to this width like this. Okay, so the central maxima is much brighter, as well as it is wider. It is twice in width compared to the other maximas. So this is what we observe. Okay, now we will make sense of this observation and we'll develop a formula for it also. Just make a note of this one. So the first calculation we will do here is we will find out position of the minimas by a sort of mathematical trick method. Position of minimas or dark fringes. By position, both we mean in terms of angular position or linear position. That is the y coordinate or the angular coordinate theta. So for that, let us imagine a sort of magnified version of the single slit that we got like this. And let's imagine that the screen is obviously much further away. So in my diagram, even though I'm not able to show it as thousands of times this, but just imagine that capital D is literally like many orders of magnitude larger than A, small a over here. So this is my single slit S, the one which is in front of the observation screen. So this one is of width E, small a. Where small a, remember, will be typically a value like 50 lambda. So order of magnitude will be type 50 times, or at least in multiples of 10 compared to lambda. So this is your small a and this is capital D. Okay. And of course, if we draw a symmetry line, then symmetry line is this one. So this is a symmetry point O, and this would be some general point P whose y coordinate is this with respect to this. Okay. So this is geometrically speaking what is happening here. Okay. Now, if we are getting at a particular point a complete dark fringe, that means light. Now you can visualize this slit as consisting of literally infinite number of such secondary point sources. Okay, but if at a particular point we are getting a complete dark fringe, that means somehow in pairs they are all cancelling each other. No other possibilities then. They have to cancel each other in pairs. Okay. So E is order of magnitude is 50 lambda. So the idea here is that if at the point P we are getting a minima, okay, then the so-called secondary point sources in the slit S must be cancelling each other in pairs. Okay. If you think about it, the easiest way to mathematically define this is that if we arbitrarily just take any two secondary point sources like S1 and S2, which are at a distance of E by 2 from each other, half. So what we are doing is we are dividing the slit into two halves. So mentally, we are dividing this slit into two halves of a by 2 and a by 2. Okay. And further, we are saying that any secondary source here has another one which is exactly symmetrically on the other side, which is at a distance of a by 2. So all secondary sources are taken in pairs at a by 2 distance apart. Okay. So now if these pairs taken in a by 2 apart, if they cancel, okay, then we will get a dark fringe. So now why I've taken a by 2 and not a by 6 or not a by 10? I'm just saying that what is the easiest way of mathematically, what is the easiest way of doing this? Yes, it's symmetric from the mid partition. So you take any point above that middle partition, there is a symmetric point below which is at a distance a by 2. So all the secondary sources in the first half are paired up with symmetrical secondary sources in the lower half, which are all at a by 2 distance. So if you just divide that slit into two slots of a by 2 each, then you can divide all the secondary sources into pairs which are at a by 2 distance each. Okay, so understood the point. Okay. So this is like a bit of a math trick that we are doing. That what is the easiest way of organizing all these points into pairs, symmetrical pairs. One easy way of organizing it is take pairs which are at a distance a by 2. Yeah, I mean that is Huygens principle application, Aditya. So obviously Huygens principle explains the phenomena of diffraction successfully. Okay. So now the light that is reaching the point P from these any two secondary sources which are at a distance a by 2 apart. So this light going here and this light going here. Okay. What will be the path difference between one pair? So for each pair which is at a by 2 distance apart, okay, at the point P, the path difference will be a by 2 sine theta, where theta is the angular position of that point. So theta is this one. Like we used to have d sine theta na, in YDSC. So just d is now replaced with a by 2. Because obviously capital D is very large compared to A. So this path difference between this one and this one we can take as a by 2 sine theta, which is then further approximated as a by 2 into capital Y, I mean Y by capital T, because sine theta is approximately equal to tan theta. Okay. अरे कैसे नहीं symmetric? Symmetric midpoints नहीं बेटा, symmetric with respect to each other. You understanding? Not symmetric with respect to the midpoint, symmetric with respect to each other. So every particle on the top half has an equivalent particle below from which it is a by 2 apart. So that's why you can count all the particles here. If there are, let's say, 5,000 particles, then there are 2,500 pairs which are such that each pair is at a gap of a by 2. If there are 5 million, then there are 2.5 million pairs where each pair is at the same exact thing. So each pair is producing exactly this path difference. So now the condition for them to cancel each other. So for each of these pairs to cancel, and therefore a dark fringe, okay, to be observed at the point P. The condition is that the delta x between each pair should be lambda by 2. so that the phase difference between light from each pair is pi. So in pairs they are all cancelling each other. So a by 2 sine theta should be equal to lambda by 2. So you're getting a very interesting this thing, that the angular position of the first minimum is sine inverse lambda by a, or we can say y by capital D is equal to lambda by a. But this is the more important thing for us now. So you can say this is the angular position of the first order minimum, or what we call the first dark fringe. Now, why this one I'm so sure is the first dark fringe and not the second or third or fifth or sixth, I'll tell you. We'll understand this as we continue this maths forward. We'll understand this. Okay. Now you can see the significance of the slit width. Okay. So the other thing you can see once you got this angular position, you will see is that if this slit S was a YDSC type slit, okay, then lambda would be, I mean, A would be approximately equal to lambda, or might even be less than lambda, or slightly greater, whatever. Okay, then theta would be of the order of pi by 2 for first minima. Okay, so that means on the screen, the first minima would be at y tending to infinity. Okay, so that is what happens in YDSC if you cover the second slit. So that is why, so this is why in a YDSC, if one of the slits is covered, okay, then we see no pattern on the screen. Instead, the screen is, okay, mostly uniformly illuminated, because the first minima, why is uniformly illuminated, is because the central maxima of the diffraction pattern, okay, spreads out to the whole screen. Okay, so in our intensity versus position on the screen graph, we would see something like this. The central maxima only is occupying the entire screen, because the first minima is at theta equal to pi by 2, no? So it's going to y to infinity on either side. So we are seeing uniform brightness more or less. So that is why we cannot use Young's double slit experiment to demonstrate diffraction. In fact, you can get this as a conceptual question. What would happen, what kind of thing you would observe if you covered one of the slits in a YDSC, in a standard YDSC? This is what you would observe. You would observe a uniform intensity throughout the screen, because the central maxima of the diffraction pattern, okay. But on the other hand, whereas in the single slit diffraction experiment, okay, your slit width is of the order of 50 lambda. So your first minima is occurring at theta of the order of sine inverse 1 by 50. So you can see it's a small theta. Okay. So accordingly, it will also be at a y which is very less compared to capital D, because this sine theta approximately equal to theta approximately equal to tan theta, which is y by d, will be of the order of 1 by 50. So this is the experiment that we want to do. We want the first minima to be reasonably close to the central maximum because capital T is very large. So that is the logic of, so that's why A should be of the order of about 50 lambda. Okay. Because then the diffraction pattern is visible clearly on the screen. Okay, so I'll just leave you with this thing to just note down the key points or at least understand the key points. You don't waste too much time writing down because sending you the notes anyway. Okay. Again, this is a conceptual type of experiment, so it will definitely help a lot to read from Resnick Halliday. Okay, so now let us move on to the second order minima, how we calculate that. Now for angular position for second order minima, we can do the next simplest thing here, that we can divide the slit instead of into two symmetrical parts. We can divide it into four slots. Okay. And divide it into four slots of e by 4 each. So then in pairs the slots can cancel each other. So the condition for destructive interference, so all pairs in the first and second quarter cancel, and again all pairs in the third and fourth quarter cancel. So we want that condition to occur. We'll see that e by 4 sine theta should be equal to lambda by 2. So we get the angular position as sine inverse 2 lambda by e. Okay. Then similarly for third order we will take e by 6. Okay. 6, okay, parts. Okay. Cancel in pairs. So we'll get the condition e by 6 sine theta is equal to lambda by 2. So this time we'll get, so you can see the trend. The angular position of the minimas is n lambda by e. So in general, minimas or dark fringes are located at theta equal to sine inverse lambda by a, second order sine inverse 2 lambda by a, third order sine inverse 3 lambda by a. So nth dark fringe is at an angular position of sine inverse n lambda by a, or y is equal to capital D into n lambda by e. And this agrees with experiment. Okay, so this is the nth order dark fringe, and we can also understand why the fringe width is the way it is. Okay, because the central maxima on the screen will now spread between the first dark fringe above and below. Okay, so whereas the second dark fringe, so the central maxima that you are having in terms of intensity is still not showing why the intensity is more for the central one and the intensity diminishes, but at least it's showing you the width. Okay. It's showing you that the width of the central maxima this will be twice of d lambda by e, whereas these ones, the first maxima, the second maxima, these will all have width of d lambda by e. It also justifies that experimental observation. This will have, so the central maxima, it will have an angular width of 2 times sine inverse lambda by a, or a linear width of 2 times d lambda by a. Okay. Whereas first maxima, second maxima, actually better than maxima we should call this the fringes. central bright fringe, the first bright fringe, these will have angular width of sine inverse lambda by a, or linear width of d lambda by a. Same like this. So hope this is clear. Yeah, Shreya, I will send you the recording today, so don't worry about the part you missed. So we have done the calculation for the second, third, and so on and so forth. The first, second, third dark fringe positions by, just like for the first order minima, we divided the slit into two equal halves of E by 2 and A by 2, and we made all pairs cancel. Now for the first order, I mean for the second order minima, instead of 2, we are dividing it into 4 bits like this of E by 4 each. And now all pairs in the first two cancel, all pairs in the last two cancel, and that's how totally we get destructive interference or complete dark fringe, where all pairs which are at E by 4 sine theta, I mean E by 4 gap with respect to each, they are cancelling each other at the angular position. E by 4 sine theta is equal to lambda by 2. Now similarly for the third order, we divide the slit S into 6 equal bits of E by 6 each, and then we make, so these 6 bits are in 3 sets of pairs, and all sets of pairs cancel each other. So the condition becomes this, that theta sine inverse 3 lambda by a. So like that, if we carry on this trend, we see that the general condition that we get for the nth order dark fringe, the angular position is sine inverse n lambda by a, where n goes from 1 onwards, natural numbers. And from that, if we visualize the intensity versus the position on the screen, you can see the central maxima or the central bright fringe will basically spread between the first dark fringe above and below. So that's why the width of the central maxima in terms of angular width as well as linear width is coming out like this. Whereas the first bright fringe will spread between the first dark fringe and the second dark fringe on either side. So that will have a width which is half of the central maxima's width. Okay. So once we have got an idea of the position of the minimas by this kind of, sort of shortcut clever mathematics, now we are in a position to develop the maths for the proper understanding of intensity with respect to angular position, or intensity with respect to the y coordinate. Okay. So the next part is a little bit complicated. It'll just take few minutes, 5 minutes or so. But the thing is, the derivation is not in your syllabus because obviously it is only JEE mains. So once again, to emphasize, this single slit diffraction experiment and the concept of diffraction itself is only part of your JEE main syllabus, not part of your JEE advanced syllabus. Hence, only formula based questions. Okay, so you need not know the derivation, but we will understand the derivation for your overall understandings case. Okay, so the general formula for net intensity as a function of angular position theta, or a function of the y coordinate. How do we do that? Okay. So the basic idea is the same. We will imagine that we are dividing that slit, but this time instead of dividing it, in that manner into symmetrical pairs kind of things, we will now divide it into infinite number of point sources, secondary point sources, which are at some kind of very small distance with respect to each other. So imagine this slit consists of n number of point sources, very large number of point sources, okay, such that if the slit width was E, now the distance between any two consecutive point sources, we can take that as a delta D. So delta D is equal to E by capital N, But now we are going to apply the limit that capital N tends to infinity. Okay. So what we are doing conceptually here is that we are dividing the slit into infinite number of point sources, secondary point sources, and then we are taking delta D. So the slit, it consists of n tending to infinity number of secondary point sources. So actually this should be some n plus 1 or something, but since n is tending to infinity, so it doesn't really matter. So this is the distance between two consecutive secondary point sources. So now when light is traveling from all of these to a distant point on the screen, which is at an angular position theta. So at position theta on the screen, the phase difference between two consecutive point sources, okay, secondary point sources. So if we write that as delta phi, it is going to be how much? It is going to be 2 pi by lambda into delta d sine theta. Okay. So that is going to be 2 pi by lambda into e sine theta by n under the limit that n tends to infinity. Okay. So now suppose if each secondary source produces an amplitude, an electric field amplitude of E naught, then our phasor diagram looks very interesting. It looks like a chain because there are infinite number of phasors. Okay. So then the net amplitude E net will come from the phasor summation of the amplitudes E naughts from capital N number of point sources, secondary point sources. Okay, such that the phase difference between any two of them is this delta phi. So your phasor diagram will look very interesting. Your phasor diagram will look like this, that you have a series of phasors like this, and each one is progressively at a phase difference of delta phi. Okay, so each of these is delta phi. So I'll just draw as if it's a magnified version of that diagram I've shown. So this is one of the phasors, then the next phasor is slightly at a phase angle to it, then the next phasor is at a slight phase angle to that, and the next phasor is at a slight phase angle, and like this there are infinite number of them. Okay. But then each of the phasors is also very small because it's a secondary source, so it's creating amplitude which is very small. And delta phi is also very small, no? Because n is tending to infinity. So each of these angles is very small and each of these amplitudes is very small. So in a proper diagram where you have not magnified it, this will look like a curve instead of looking like the side of a polygon. This phasor diagram will ultimately look like a curve like this, where in this curve you started with a small phasor here. Okay, so this was the first phasor, and you ended up with the last one over here. this is the nth one. Okay, and in between you have all of these. So now if you just geometrically construct this, okay, drop a perpendicular from here, that is from this one we dropped a perpendicular. Like this, if you drop perpendiculars from all of them, they will all intersect at a point, including the last one. So you drop a perpendicular from the last one. So wherever they intersect, that is like the center of curvature of this chain of phasors. So this is like a chain of n phasors of e naught each. Okay. So this angle, suppose this is some alpha. So this angle will just become n times, capital N times delta phi. So alpha will become capital N times delta phi. So it will become n into from above 2 pi by lambda e by n sin theta. So even though limit n tends to infinity, but n cancels out. So ultimately this angle in between is independent of that. It is 2 pi by lambda e sin theta. That is this angle alpha. Okay. And if this has some radius of curvature, you can see that the arc length, that is n e naught. So the radius r is equal to, okay, on this. So this is the maximum net amplitude, which is for the central maxima. So at central bright fringe, what is happening is that theta is 0. So delta phi is 0. So your phasor chain is just going to look like a straight line. Okay. So your phasor chain will look like, this is the nth one, this was the first one. So your net amplitude is going to be the central maxima, and that is going to be n times e naught. Okay. So this, that's why this is n e dot is, okay, this. So it is E max by alpha. That is the radius of curvature, where E max is the central, okay, it is the maximum amplitude at central bright fringe. Maximum net amplitude at the central bright fringe. So just make a note up to this, and we are almost at the end of the derivation. So you see very interesting derivation. Now in this diagram, what is your net amplitude? Your net amplitude is going to be this one. It's going to be this phasor. So it's going to be the chord of the circle. Okay. So now the E net at that angular position theta, it is going to be this, which is basically 2r sine alpha by 2. So you substitute the value of r from here, and you can see it is becoming E max. This. So that is why you get that sine hyperbolic function. Okay. So what we get is the net amplitude at any point is E max into, we can say, sine beta by beta, which is the sine hyperbolic function, where beta is nothing but alpha by 2. Okay. Where beta is alpha by 2, and alpha we have seen earlier, so it is nothing but pi by lambda a sine theta. So now it's very easy for you to trace also that where all this will be 0. It will be 0 where sine beta is 0, but beta is not 0. So that is where a sine theta is equal to n lambda. And that's exactly what we had got for the minimus. That theta was sine inverse of n lambda by a. So this derivational approach, where considering infinite number of point sources and the addition of infinite number of phasors in a chain like this, and you're using calculus effectively. But because it's basically like a, each of these is a differential amplitude which you're adding. So those differential amplitudes all added together, they're becoming a curved chain rather than like the sides of a polygon. And now you know that intensity is proportional to square of amplitude. So that's why your intensity formula is like a sine hyperbolic square formula. And that is why the graph that we had plotted earlier is a sine square hyperbolic function graph. Sine square theta upon theta square type of graph. Okay, so I'll just take you to the top of this once. Okay. Let's just take another few minutes, 5 minutes or so, don't worry. Okay, so now this is just geometry. Remember that this is not an actually significant quantity other than the E net. This radius of curvature and center of curvature, they are just geometrical drawings because we have arranged the phasors like this. So they are forming the sector of a circle, a curved path like this. So it has a center of curvature, it has a radius of curvature. So that is R and that is C. So they are just geometrical quantities. They don't have any real significance. But the E net is the important thing, which is the chord of the circle here, which has the uh, significance. So now drop this perpendicular from here, and it's an isosceles triangle. So you know that formula of the chord length. It is 2r cos of sorry sine of half angle. So the angle subtended by the chord of the circle is alpha. So half angle is alpha by 2. So it becomes 2r sine alpha by 2. Now here what is r? R doesn't have any significance on its own. R has to be expressed in terms of this chain length, which is nothing but the sum of the individual amplitudes or the maximum amplitude. So that is n e naught by alpha or e max by alpha. So from that you get this sine hyperbolic function. Okay. So now just square this function on both sides. So you get, so because intensity is proportional to square of amplitude, so therefore the net intensity will become the central maxima's intensity into this sine square hyperbolic function. So this is the important formula, and this is the formula whose graph was what we got, where beta we can write as pi by lambda a sine theta in terms of angular position, or we can also equate it with pi by lambda into y d by a, because sine theta can be substituted as y by d. So it is this. So basically you can see beta is proportional to y. So that is why when we had plotted the intensity versus y, we had basically got a sine square hyperbolic function. This sine square hyperbolic function, if you study in maths also, it has this property that this width, this one, is double of this width, and the peaks go on dropping very rapidly. There's in fact a ratio for it and all that also, if you study it mathematically properly. So you can see that I net will be 0, that is minimas, at beta equal to pi, 2 pi, like that, n pi. So that is pi by lambda a sine theta equal to n pi, but n not starting from 0, n starting from 1. So that is what we had got. Theta is sine inverse of n lambda by a. Yes. But in between these, at certain arbitrary positions, the maxima is there. Now I won't get into those arbitrary positions, because then that becomes like a real hardcore mathematics application for sine square hyperbolic function. Is not one of the standard functions that we do at 10 plus 2 level. So all that in-depth analysis is not required, but because that's not part of your math syllabus in calculus also, I think sine square hyperbolic is not in detail there, just the basic graph and the understanding of it. Okay. And also you can see that for beta equal to 0, beta tending to 0, so that sine square hyperbolic function tends to 1, because it's sine 0 by 0, that limit. So that is the central maxima. It's to 1. Okay, so therefore I net is equal to I max at theta equal to 0, which is basically beta equal to 0 or y equal to 0. Okay, so that is the central maximum. Okay, people. So with this, we conclude the single slit diffraction discussion and concept. Okay. So I've explained to you in detail how this works. But as I said, that for the exam level in JEE mains, you just need to remember the sine square hyperbolic function, and you also need to remember this formula for the minima's position, that is sine theta is equal to n lambda by a, or theta is equal to sine inverse n lambda by a. These are the two formulae you need to remember. The derivation and all is not important, because it's JEE mains, so it's only formula based questions. Okay. So, right, people, that's it from my end for today. And with this, we finish wave optics. So, we will do a discussion of few questions if required next time, especially if you have doubts and things. But we are now in a position to start modern physics, and modern physics is very, very easy. Mostly, we will be doing the previous year JEE questions in class itself, and with that, your preparation for modern physics should be done. With just a little bit of extra work from your side at home, your modern physics will get done. So you can start planning your revision of physics from from now on, especially if you're doing revision of mechanics and all that. It's a good time to start. So anyhow, that's it for today, people. All the best.